In this recording, we'll work on a few examples. Okay, let's start with this one. So we have a train locomotive of a mass of 15,000 kilograms. It is moving north at 15 meters per second when it encounters and collides with a stationary locomotive of a lesser mass of 10,000 kilograms. The first question is, what is the initial momentum of the first locomotive? Okay, so anyway, it makes sense to draw what we have. So what we have is a train. That's one locomotive, and that's the second locomotive. Okay, this is moving with a velocity v. That one is at rest. They're moving north. Now they're asking us about the momentum of the first one here. Momentum is, remember, mass times velocity. So if we choose the north direction as positive, then my momentum of the first locomotive, let's call it P1, is going to be 15,000 kilograms times 15 meters per second. So that's going to be 15,000 times 15. So that's 225,000 kilogram times meters per second. Notice here we don't have a special unit for momentum. We just use kilograms times meters per second. We don't have a special unit. Okay, the second question, what is the initial combined momentum of both locomotives? To find the combined momentum, so let's call it PC, is going to be P1, momentum of locomotive 1, plus the momentum of locomotive 2. Now locomotive 2 is at rest, so its momentum is 0 because it is at rest. So their combined momentum is also equal to P1 in this case. (225,000 kilogram meters per second). Okay? Now, then what is the combined momentum of both locomotives after the collision? So the combined momentum here that we just calculated is before the collision. What's going to happen after the collision? That's the key word, conservation of momentum. Since momentum is conserved, I don't have to calculate anything now. We have it already. The combined momentum after is going to be equal to the combined momentum before, which is equal to 225,000 kilogram. Actually, I have it written wrong here. Meters per second. That's my combined momentum of both locomotives after the collision. Now they tell us if both locomotives get tangled up in the collision and move as one object, what's their resultant velocity after the collision? Okay, now we know their momentum. This is their momentum. And momentum is mass times velocity. Notice this momentum is positive, meaning its direction is along the north. And it is equal mass times velocity. They are moving as one. What does that mean, moving as one? Their mass is going to be their combined mass. Meaning, I can write this as 15,000 kilograms plus 10,000 kilograms times V. And my only unknown then is just V. So V, okay, let me add another step. So this is going to be 25,000 kilograms times v. So I can just find v by dividing 225,000 kilogram meters per second. Let's separate the things by 25,000 kilograms. Okay, so that will give me my final velocity, which is 9 meters per second. Okay, that looks like a tricky problem, but it's simple. Again, to summarize what we had to do, we had to make a drawing of the situation. We figured out the momentum of the first one, it's mass times velocity. We took the positive direction as the north, so that momentum is positive. The momentum of the second one is 0 since it's at rest. So the overall momentum is just equal to the momentum of the first one. After the collision, they are going to move as one. So we combine their masses. The sum of the masses times the velocity is my new momentum. The key point is the momentum before the collision is equal to the momentum after the collision. Okay, let's work another variation of this problem. Now in this case, what we have is the same trains, the same locomotives. However, okay, let me make the drawing here on top so we don't use as much space. Okay, so this one is moving in the forward direction at 15 meters per second and towards the north, and this one is moving south at 10 meters per second. Okay, now the question is, what is the initial combined momentum of both locomotives? So momentum before of both locomotives is going to be momentum of locomotive 1 plus momentum of locomotive 2. Now, when we take the positive direction in the forward along the north like we did last time, then momentum 1 is going to be 1,500 kilograms times plus 15 meters per second. And then momentum 2 is going to be 10,000 kilograms times the velocity, which is 10 meters per second in the negative direction, so it's minus 10 meters per second. So my overall momentum before is going to be 225,000 kilogram meters per second minus 100,000 kilogram meters per second, which is going to be equal to 125,000 kilogram meters per second. That's my combined momentum before. Now they are asking us, if they get tangled up, what would be the resultant velocity after the collision? Okay, now, what do we know is that's going to happen during the collision? We know their momentum after the collision is going to be the same as their momentum before the collision, which is 125,000 kilogram meters per second. So what that means, after the collision, this tangled up mass of two locomotives is going to have a positive momentum, because we found a positive momentum for the combined momentum of both of them. Now, so what's the velocity? We know that momentum is given by mass times velocity. In this case, the mass is going to be the combined mass of both of them, which is 15,000 kilograms plus 10,000 kilograms, so which is 25,000 kilograms. times my unknown velocity. And we solve for the velocity, so it is 125,000 kilogram meter per second divided by 25,000 kilograms. And that gives us 5 meters per second. That's my final answer. Okay, let's work another example. We have a car with mass 1200 kilograms driving north at 40 meters per second and turns east driving 30 meters per second. What is the initial momentum of the car? So it's easy. Initial momentum of the car, mass times velocity. Now in this case, we have the mass is 1200 kilograms times 40 meters per second. Okay, now since we have north and east, I'm going to say north. So what we have here, 48,000 kilogram meter per second towards the north. That's the initial momentum of the car. What is the final momentum of the car? Final momentum of the car, again, mass times the velocity of the car. In this case, that's going to be 1200 kilograms times 30 meters per second east. Okay, now notice here that we are along the east, so 30 times 12, so that's 36,000 kilogram meters per second east. Okay, this is very important. That's why I put the directions different. Now the key here, what's happening? Remember, we have to treat momentum along separate directions. North-south direction has to be treated separately from the east-west direction. I'm not sure what happened to the east there. Okay, which means, what was the initial momentum of the car along the north? 48,000 kilogram meters per second. What is the final direction of the car along the north? 0. It's not moving along the north anymore. And we can treat the same thing along east-west direction. What was the initial momentum of the car along the east-west direction? It was 0. There was no motion in the east-west direction. What is it along the east-west direction at the end? 36,000 kilogram meters per second. So what we need to do for the change in momentum, we need to write them up here. For example, in the north-south direction, what we have, so we are looking for change in momentum. We have a final momentum of 0 and an initial momentum of 48,000 kilogram meter per second. So the change is minus 48,000 kilogram meters per second. In the east-west direction, my change in momentum, again, same thing, P final minus P initial. However, my P final here is 36,000 kilogram meter per second, and my initial is 0. So my change is 36,000 kilogram meter per second.